Hello! The goal of this media is to both explain the complexities of a dye-sensitized solar cell, as well as guide you through the process of creating one. First, I want to briefly explain the science involved here. Solar panels work because of a special type of metal known as a semiconductor. The outermost electron of a semiconductor can be dislodged with sufficient energy. In many cases, the energy contained by a ray of sunlight is capable of knocking this electron off of the atom. A solar panel harnesses this power by using an anode and a cathode, which create a magnetic field as the electrons are knocked off. And these drive the electron through a circuit, which then charges a connected battery, and then returns the electron to the atom, where it's ready to be knocked off by the sunlight once again. Next, I want to go over a list of components necessary to build the cell and how to obtain those components. So the first and trickiest component you'll need to find is conductive glass. Conductive glass is the shell of the panel, and it creates the form of the whole piece. Conductive glass generates a circuit, allowing the electrons to flow across the glass while still allowing light into the panel and therefore allowing the semiconductor reaction to occur. Conductive glass can be directly purchased, though it often costs a significant amount of money, and it can also be salvaged from old LCD screens, and this is usually in the form of old TVs and computer monitors. And I'll go more in depth into how these can be broken down later. Titanium dioxide serves as the semiconductor throughout this process and is the most accessible semiconductor available. So therefore it is the material of choice for the accessible solar cell. Um, titanium dioxide can be directly purchased at a very cheap price. It costs about $5 for a pound, and a pound is significantly more than is needed for a simple cell. Up until very recently, it could also be extracted from donuts through a process of heating it up to eliminate the sugars and adding other ingredients which would help remove the fats. But um, titanium dioxide is being rotated out of the available of the purchasable donuts. So now to get it for a solar panel, you just have to directly buy it. On its own, the titanium dioxide does not absorb enough energy from the sun in order to trigger the reaction, and so it is necessary to dye the titanium dioxide a deeper shade so that it can absorb more energy from the sun and therefore trigger that reaction. And so a number of materials can be used to dye it, ranging from berry juice to hibiscus tea to even ground up leaves can all dye your titanium dioxide a shade capable of absorbing that energy from the sun and triggering that reaction. The cathode is a catalyst which accelerates the electron transfer. Compared to the titanium, only a tiny amount of this is needed. The most common material for the cathode is going to be platinum or carbon. However, platinum is going to be very expensive and requires a whole process to sinter it to the glass. However, carbon is very easy to obtain. You can apply it by holding the glass over a candle, or it is as simple as drawing on it with a pencil to deposit a layer of carbon. If the conductive glass connected to the cathode and the conductive glass connected to the anode are touching, it will close the circuit and therefore prevent it from drawing anything into the battery that's they're trying to charge. And so these pieces of glass can't touch each other. And so we need to have something in between the anode and the cathode that will allow them to conduct electricity across. And so we fill this gap in between them with a electrolyte solution, which allows the electrons to flow across that gap. Usually a very, very small gap, only the width of a piece of tape, but we still want to ensure maximum conductance across that. So we'll fill that with an electrolyte solution to ensure that we can have electrons flow from the anode to the cathode and from the cathode to the anode. And so we're going to fill it with an electrolyte solution, and as seen in the image, there's a number of things that you can use for an electrolyte solution. You can buy an iodine solution from a lot of pharmacies, and that's usually not terribly expensive and is very effective at this. There's other less effective ways of doing it. One of them being salt water, which works, but it can degrade the titanium dioxide to have water in there for too long, so that's a last resort option. Next, I would like to go over the steps we will take in order to create this piece. First, we are going to take apart one of the monitors to isolate the conductive glass inside it. Each model of monitor is going to be a little different in the way you take it apart, but they will all more or less follow the same strategy. We'll start by taking off all of the screws on the backs and then also removing any plates we'll see there, such as these black ones on the left and right. After this, I removed the black perimeter plastic protecting and keeping the screen in place. Once the screws were out of the way, I was able to stick an X-Acto knife in between that back panel and the front plate and pop it off. And then with a couple more screws unscrewed and a couple plugs unplugged, I was able to take off that circuitry from the back, and you are just left with this panel. And that is the panel that I am working on in this clip. The glass that we are looking for is contained within this panel, and we are trying to pop it out, as we see there. As the glass is popped from this protective panel here, you'll notice that it's actually two pieces of glass adhered together, and one of these is the conductive sheet that we need, and one of them is just a piece of glass. And in the next step, we will have to separate those pieces of glass which have been glued together from one another. There is a protective layering on each of these glasses, and here I'm working to remove that, as it makes the glass much easier to cut later and also allows more light through if it's been removed. In this clip, you'll see I'm trying to work an X-Acto knife blade in between the two panels of glass, and I had about a 7 out of 10 success rate with this as far as monitor screens went. I had a lot of trouble working that knife blade in between the two layers of glass, and usually it would come as like a revelation moment. Like you'd be working at it, you'd be working at it, you'd be working at it, and then all of a sudden it would click, and the knife blade was just in between the two layers of glass, and then you would work the knife around the perimeter of the glass, and then the two sheets would just come right apart. Unfortunately, in this clip I've recorded here, that moment never clicks, and the glass actually ends up breaking, which happened probably 30% of the time. And you can still salvage a good amount of glass from this process if it does shatter, as you'll see in this clip. You'll see that eventually I was able to get my knife in there and finally separate these two pieces, albeit of course there were some cracks in it that I needed to work around. As you can see here, I'm kind of working around the the layer still on that glass. And it makes it much easier for the glass to break. And I had a lot more trouble working with it when that layer was there. As you can see, I'm breaking it off and having to cut around the edges there. So removing that layer beforehand is often very prudent. Um, Additionally, as that film layer is removed, the glass is very prone to breaking, and you want to pull on that glass, or you want to pull on that film as parallel to the glass as possible to prevent as much force in the perpendicular direction to the glass as possible, because that is what's really going to break it, is if you try to pull up on that film as you're pulling it away from the glass. That is what led to a lot of the breakage over the course of this project. After this step, it is often wise to use a glass cutter to cut your pane into a more usable shape, or to tape the sides even in transportation so that you don't cut yourself. The next step is conductive glass is covered with a layer of polyimide, which has to be scraped away. And I would often start this process by going over it with a razor blade to get kind of a good start on it. And then I would use a high or a very low grit, a high grit sandpaper, so that as to not scratch the conductive indium tin oxide layer beneath hand. You just want to use a very high layer of high grit sandpaper to remove the tail end of that layer of polyimide, and that will allow the surface to have a much lower resistivity and conduct the current at a much better speed. And after we've removed this layer, we are going to do a quick check of the resistance of this conductive glass. So if you look at the meter during this, you'll see that it kind of fluctuates and doesn't sit on a value. It's because it's not a it's not a perfect removal, but we'll see it sits somewhere around 50 or 60 ohms, which is excellent. Next, in a clean container, we are going to mix together 4.5 grams of titanium dioxide, 3.5 grams of white vinegar, and 7 grams of 70% ethanol. I used the basic Walgreens rubbing alcohol. For the 3.5 grams of white vinegar, we're going to perform a special operation on it prior to adding it to the solution. And in that process, we are going to first freeze, or put an amount of it into the freezer, and then wait exactly 1 hour. I put 100 grams into the freezer and waited 1 hour, and then removed it from the freezer and took only the sections that had formed into ice, put those into a separate container, let it thaw, and then used that as my 3.5 grams, because in that case we're trying to isolate the acetic acid, or have our vinegar be a stronger percent of acetic acid, which is what will help absorb and take in all of the titanium dioxide when we mix them together. And so concentrating that acetic acid is something that we want to do. Ideally, you use 100% acetic acid. However, that's a lot harder to come by, and this works just fine. Next, we'll create a perimeter of tape around where we want to deposit the compound, and then we will begin to apply it to the conductive side of the glass within that tape boundary. And then after this, we will proceed to heat it up in order to sinter the titanium dioxide together. So the process of sintering is going to heat up the titanium, and it will free up the surface free energy and bring that to a level where it can interact with itself, and it will bond the titanium dioxide together without actually bringing it to the melting point. And we do this process so that we make sure that the energy can flow between the titanium dioxide molecules. The purpose of dissolving it into this paste for the application um, ensures that there is maximum surface area of the titanium dioxide as it sinters, so that once we put this in the sun, it can absorb the most sunlight possible. I used a razor blade for the process of distribution, trying to get the layer as thin as possible without being able to see through it. Next, we are going to remove the tape and then proceed to sinter the titanium dioxide. So I found that the best way to do this is in an oven. You have to get it all the way to 450 degrees Celsius, which is very hot. And a lot of conventional regular ovens don't quite make it to that temperature. But I did have some success bringing it to temperature, bringing it as high as it could possibly go in my common kitchen oven and using that, but it is not the optimal way to do it. In this process, you'll see that I use a heat gun in order to sinter it. The small problem with that being I did this over a layer of acrylic, and it did melt the acrylic underneath, which is not desirable, and it did burn to the back of that layer of conductive glass. It should be kept at this 450 degrees for 15 to 20 minutes is the optimal time. In the next step, we are going to apply the dye. And I did this with raspberry juice. What I did is I bought frozen raspberries, and then I took a rag and put a lot of the frozen raspberries into that rag, and then I squeezed them out and let the juice drip from that rag into a container and use that. And so what I did here is I took a piece of plastic acrylic that I got from the destruction of my monitor, and I cleaned it off, let it dry, and then I put that raspberry juice on it, about a teaspoon, and then I pushed the sintered titanium dioxide on top of it, and let that soak in for about 25 to 30 minutes. And in this process, I put a weight on top of it to ensure that maximum contact between the two. I ended up giving this panel a quick clean to get off that excess dye, and then I also hit it with the heat gun just to speed up the drying process, but you can also let it air dry. In the next step, we are going to deposit the carbon onto the opposing side of the panel. And for this process, I just used a pencil and literally just drew on that other piece of conductive glass I have on, once again, on the conductive side. And you want to create just a really thin layer of pencil lead, which is going to act as our catalyst and speed up the whole process and make sure that we create that circuit. In this next step, I'm going to use double-sided tape to create a perimeter around the dyed and sintered titanium in order to adhere the two panels together and also prevent them from touching one another or the electrolyte solution from escaping. The reason we don't want these panels touching each other is because if the two layers of conductive glass are in contact, that will complete the circuit, and we won't be able to capture the energy created by this process. Finally, we are going to apply the iodide solution and complete the final circuit. So for this, I used Walgreens Basic Iodine Solution. You can buy this at Walgreens, but you can buy an iodine solution at pretty much any pharmacy. It is used to treat wounds, but it is also used as an electrolyte solution in dye-sensitized solar panels. So we are going to apply maybe a quarter teaspoon of this to the carbon layer, the pencil layer of conductive glass, and then we are going to adhere the two together using the two-sided tape, and we're going to seal it off. After we do that, we are going to attach a clamp to both the top and the bottom layers of glass. I prefer to attach this clamp on the broken sides of the glass. I found that that is much more conductive when using monitor glass. And so as you can see, I leave a little top tab open and a bottom tab open so that we can attach our gator clamps there to create our circuit. So I'm just pushing the two together and ensuring that that tape is sealed here in this clip. Unfortunately, by the time I had the equipment and time to record this video, the school lab was closed, and so I had lost access to the ammeters that they had there, so I couldn't, this portion of the video, I had to wait for the dye to dry, and I no longer had access to the meters, so I wasn't able to actually get a final reading on this panel. But here you'll see I'm just distributing that dye in there, or that's not the dye, sorry, that is the electrolyte solution, and then I'm going to attach the clamps to either of these tabs, and then were you to hook this up to a battery or a light or pretty much anything to complete the circuit, you could also just hook it up to the meter and test the voltage created by the two panels. I was really happy with how this product turned out, and although the particular one I recorded for this video I wasn't able to check how much voltage it pulled, on my most powerful solar panel I was able to pull about 0.4 volts per square foot, which is about a third of the power of one of the portable solar panels you can buy off a site like Amazon. And so I was really satisfied with that result, although that was only in a very small rectangular area, and then I did the math to figure out the volts per square foot. But actually creating and pulling that voltage from a square foot would have been very difficult given these items. Moving forward with this project, I would like to maybe try to reiterate that same voltage potential over the course of an entire square foot. Other things I'd like to do would be to optimize the numbers and really figure out exactly how much paste you want to apply per square inch. Because if too much paste is applied for the sintering step, it will actually just flake off and you'll lose all of it. So you want to just have enough that it sinters without crusting up and flaking up and falling off. So there is a special spot there. There is a sweet spot, and I haven't found it yet. And so finding that sweet spot of just how much paste to apply, and then also really figuring out that ratio of acid to titanium to ethanol, because I really only did that for 3 or 4 iterations, and that's not nearly enough to find any conclusive data on what works best. So thank you so much for watching this video on solar panels, and I hope you learned something today.